All right. I know folks will probably continue to join us, but I'll go ahead and get started just with introductions. So welcome again, everyone. It's great to see you all here today. So part of the UC Love Data Week programming, this is a Getting Started with Network Data using Geffy workshop offered through UC Riverside Library. I'm going to share the link again in chat. That goes to a Google Drive folder that contains a link to these slides for reference. There's a lot of tutorials and resources and other links and things shared in the slide deck that may be helpful for you to reference, as well as to some sample data sets. If you're new to using network data, if you don't have your own data already, but want to see what the affordances are of this tool, Gephi, or what network data looks like, there's a couple of good examples in there for you all. So before we dive in, I do like to start with this statement of solidarity. So I want to acknowledge that the pandemic and other structural inequalities have disproportionately affected people of color, particularly Black and Indigenous folks. So as a member of the UCR community, I stand with Black Lives Matter and AAPI communities against racism, xenophobia, and human rights violations. I also want to recognize our responsibility. I'm located here in Riverside, California. So I want to recognize my responsibility to the original and current caretakers of this land, water, and air, the Cahuilla, Tongva, Luiseño, and Serrano peoples, as well as their ancestors and descendants, past, present, and future. And though we now are meeting in a digital space, I invite you, if you're not familiar, to learn whose ancestral lands you're physically located on, wherever you are. At the website is one example on the screen, native-land.ca. And definitely for this workshop, do whatever is best for you. Feel free to engage any way you're comfortable. If you'd like to have your video on, if you'd like to ask questions in chat, very open to any form of participation. And I am available kind of to follow up if you have questions afterwards. After we turn off the recording, I'll stick around for a few minutes if folks have kind of follow-up questions as well. So I'm Rachel Starry. I am the Digital Scholarship Librarian here at UC Riverside Library. And the goal for today, we're only together for an hour and a half. It's not too long. So I'm hoping to just, and knowing too that folks are coming from a lot of different backgrounds and disciplines, the goal here is just to kind of give you some essential resources related to the vocabulary, the terminology, concepts that are commonly used in network science when we're talking about network graphs and performing network analysis or analyzing network data. And the particular tool that we'll be kind of playing around with today is called Gephi. It's a common tool in the humanities, but I recognize it is just one tool out of many. So again, the goal isn't necessarily to gain deep familiarity with this particular tool, but more to kind of demystify it. If you're new to network analysis, what are the ways that this particular tool, like other tools, can allow you to get started analyzing network data? What does that look like in the tool, as well as how can you use it to visualize networks? Again, I know folks have continued joining us. Here's a link again to the slides, some sample data sets, and all of that. So I would love to hear from you all. Where are you joining us from? I'm hoping we have folks from across the UC system. If you're comfortable sharing, as you're comfortable sharing, let us know in chat where you're coming from, why you might be interested in this topic, if you already work with network data, maybe what discipline you're coming from. But it would help me too to kind of know where we're at in terms of folks' interests and levels of experience, perhaps. But we'll be going kind of for a general breakdown today. So no experience is a perfect place to be joining from. Awesome. Already folks from 3 different UCs representing a range of experience. So some folks who are saying no experience, a couple studying data science, some familiarity with network data, social science, business analytics. Looks like quite a variety. Awesome. And ecology and environmental. Okay. So we have a number of data sets too today that we can kind of play with. So it'll be interesting to see when we get there. Maybe I'll do a quick poll of the room to see which one we dive into. Awesome. Oh, a lab that uses Gephi. Okay. So this is great. This is great to hear. So looks like we're mostly in the same boat of learning this, maybe a little bit of experience here and there. So that's great. That's very helpful to know, and welcome again, everyone. So yeah, networks. Essentially, and I like to start off here kind of what is a network, and then what is network analysis, and then we'll look at a couple of the different research questions that folks who study networks commonly ask, and then we'll get into kind of examples of network data. What does it look like? What do network graphs look like? And what can we learn from them? So networks are just all about relationships between things, people, places, ideas. You can really use networks to study and understand a variety of kinds of relationships. And network analysis is just, that's all that is really. So honestly, if we're talking about one network, we might have questions about the composition and structure of one network, but a lot of times we also want to compare one network to another network. So we'll talk today about some kind of specific formulas and metrics that we would perform on individual networks, as well as some that are kind of network level for comparing across multiple networks. So every year I wonder, what year is this going to become a very outdated example? But I'm hoping it's not yet. I love to use this example of the 6 degrees of Kevin Bacon when I talk about network analysis. So this is a game that I remember playing over a decade ago, washing pottery off on field school. My background's in archaeology. So it's a parlor game played kind of based on this 6 degrees of separation or small world concept. So essentially you kind of ask, well, you know, the concept is Kevin Bacon has been in a lot of films, and he may or may not be close to the center of this kind of imagined Hollywood network. So if we take, for example, this example network on the screen here, there's 3 what are called nodes. So we've got Kevin Bacon, Charlize Theron, and Samuel Jackson. And we can draw edges based on any kind of relationship. So in this case, these are actors that have acted in a movie together. So we've got Kevin Bacon and Charlize Theron both acted together in Trapped, and Charlize Theron acted in Astro Boy with Sam Jackson. So a network is made up of nodes and edges. In this case, the actors are the nodes, and the edges, we've decided to draw an edge wherever the actors have appeared in movies together. And edges can be explicit or they can be inferred. So there's often a decision-making process that goes into the construction of edges, although in some cases, edges can represent literal connections like power lines or roads or other things. Another key concept and term that I'll be using a lot today is degree. So the degree of a node is just the sum of edges connected to it. How many edges are connected to it? So in this very simple graph, Kevin has a degree of 1, Samuel has a degree of 2, and Charlize has a degree, has a degree of 1, and Charlize has a degree of 2 because she's connected to both the other people on the graph. This is a very kind of important concept that a lot of the other kinds of network metrics will build upon. So, like this idea of Hollywood actors having a Bacon number representing how many hops away from Kevin Bacon are they in this Hollywood social network, there are many different ways to calculate the importance of nodes and to quantify those relationships between them. So that's kind of very high level, my favorite metaphor to use when we're talking about what is network analysis. And there are a lot of different topics and subtopics. I mean, network science, like data science more broadly, is a huge field of ongoing research. And it's applied very differently across different disciplines. But there are some common questions that folks in particularly the humanities and social sciences, but other disciplines as well, often ask about networks that they're studying. So one of these is, what are the most important people, things, ideas, whatever, nodes in my network? And of course, importance can be defined in drastically different ways. So we'll actually spend a lot of time talking about that. The second question is, how strongly connected is my network? Is it loose? Is it dense? And then thirdly, another very common question is, are there detectable groups or communities or clusters of nodes in my network that are maybe more strongly connected to each other than to the larger network? So those kinds of questions correspond to 3 pretty common methods for analyzing networks. And that is calculating network centrality to determine what are the most important nodes in a network. Again, importance being with a big asterisk next to it. Hard to define. Calculating network density, which describes the shape and overall connectedness of a network. And then calculating modularity. That's just the fancy network science term for whether and how nodes cluster into groups or communities. There are so many examples of how network analysis has been applied across different fields of research. It's really quite difficult to just focus on a few examples, but I've called out here a few, and I've got links out to articles and publications and like even some Wikipedia pages embedded in here. Again, if you access the slide links. So in terms of common use cases, we're talking about things like infrastructure vulnerabilities, complex species interactions in different kinds of ecosystems, social networks, which are as applicable to folks in literature as they are to epidemiologists, citation analysis, social media analytics, both on the tech side of things, as well as the kind of understanding collective behavior side of things, as well as many other kinds of networks. And networks, of course, of historical or literary relationships. Again, social network analysis is one of the most well-known applications across disciplines, but it is by far not the only one. And again, it's really hard to overstate how embedded this field of research has become across different disciplines, which I'm excited to see kind of represented as well in this group here today. All right, so the first question here, what are the most important nodes in my network? So we'll actually spend quite a bit of time talking about different ways to calculate the importance of nodes. And a lot of those refer to different types of centrality. We'll get into a little bit of graph theory, just a tiny bit, hopefully not too much. So essentially, the issue here is that important, right, can mean a lot of different things for a lot of different kinds of networks. So for a social network, we might want to know which person has the greatest number of followers or friends. A high degree, again, simply counting how many edges a node is connected to. Or if we're studying other kinds of networks, perhaps a supply chain or transportation network, or even a power grid, a highly connected node might be a spot in the network where targeted efficiency of improvements could have the most gain, or where interruptions could cause the most damage, and perhaps even cascading failures across the network, like we've seen with power grids and regional blackouts or brownouts. So centrality scores can actually be measured lots of different ways. And we can ask this question of which nodes are important in several different ways. We'll just talk about 4 today. There are more than that, but these are kind of some of the main centrality scores that you may want to be aware of. So again, these are just different kinds of network centrality. So the first kind, degree centrality, is also the most straightforward. So this is the simplest measurement of network centrality. And it simply measures how many edges each node is connected to. This is particularly useful as a measurement in more complete social networks to find very connected individuals, people who are likely to hold the most information or who might be able to quickly connect out to the wider network. A really fun example of this. So Evelina Gavasova is a data scientist at the Turing Institute, actually. And she created several different networks for characters in the Star Wars universe. So this one here, she has a really wonderful example and kind of walks through, she's created networks for each of the first 6 films. You know, in this blog post, she kind of gets into how she calculated edges. Again, a decision had to be made. I think in this case, the decision was made if 2 characters speak in a scene together, then an edge is drawn between them. So in this example, in the Star Wars prequel trilogy, episodes 1 to 3, Anakin Skywalker, who's, you know, the protagonist, has a high degree centrality score across all 3 films. This makes sense for a character that is on screen a lot. And he, along with Qui-Gon and Obi-Wan, have the highest degree centrality scores across all 3 films. They obviously have the most direct connections to other characters in these films and are therefore important to the film's social network in that way. A caveat for using degree centrality scores, they don't work well for ego networks. An ego network is simply a network that is organized around a single individual. So for example, the letters sent and received by one person, you know, in their lifetime, or somebody's social network from Facebook, your friend network. Obviously, the person the network is organized around is going to have the highest degree, and that's not going to tell you anything very helpful. And in fact, you're not going to learn perhaps very much about other people's connections to each other in an ego network, because it really is just identifying the relationships between one individual and other individuals. Similarly, degree isn't ideal for a social network derived from literature. And this is partially true for film as well, right? Where the main characters in a novel, play, screenplay will statistically appear with more people and have higher degrees. So there's a pretty close correlation between degree centrality and the frequency of character occurrence just on screen or on the page. So that's a caveat for this one. Another kind of note about degree centrality, it can be nuanced if your network is what's called weighted or directed. So degree is simply the count of edges in an unweighted, undirected network graph, or network. But when edges have weight, it's common to combine edge weight with degree to get what's called weighted degree. So in this example here on this slide, you might consider the example on the bottom where you have a weighted graph here. Imagine that these were co-publications or co-authorships between authors B and C published together, twice, but authors B and A published together 4 times. You could combine the edge weight there with degree to get a more accurate representation of degree centrality using that weight. And then similarly, it's also possible to combine degree with direction if you have a directed graph. So in the case on the bottom right here, we might imagine these are letters being sent to and from different places, or perhaps flights from one city to another. So in this case, you would have what's called in degree and out degree in order to kind of give additional meaning to graphs that are either directed or weighted. Another common type of degree centrality is called betweenness centrality. So this is a good way to find which nodes are the most important for holding a network together. So this measure looks at how many shortest paths across the network lead through each node. So a shortest path across the network is just how many hops does it take to get from one point to another. So if you imagine, one node, how many shortest paths across the network pass through that node, that node's going to have, if has a high betweenness centrality, then that node is central in the sense that it is controlling a lot of the traffic across the network. So if we imagine another Star Wars example, for example, if you were Leia and you wanted to send a message to Greedo, with whom she never, appears in the scene, she would have to send that message through Han Solo because he has interacted with both Leia and Greedo. On the other hand, if Leia wanted to send a message directly to Luke, who she has appeared in scenes with, she has a direct connection. So the betweenness centrality for Han is computed using the number of shortest paths between all the other characters, including that one between Leia and Greedo, that pass through him. And another example here, actually, if we go back to the Star Wars example, we can look at the difference between degree and betweenness scores. So we saw that Anakin, as the protagonist, appeared in a lot of scenes and spoke to a lot of people in episodes 1 through 3, but he does not even appear on the top 5 list for betweenness centrality scores for episodes 1, 2, or 3, because he is not a connector in the social network of the Star Wars films. Let's see, question in chat. Why are some betweenness values not integers? Which ones? So you can normalize betweenness values between 0 and 1. Is that what that question is about? Like when you see betweenness values in the wild in research? We can maybe follow up on that later when we're kind of playing with it in Gephi as well, because that we'll get into that as well when we're actually looking at Gephi. You have the option to normalize different kinds of centrality scores rather than having the absolute value of the score, which is of less comparative value, of course. All right, so betweenness centrality is an excellent score to look at for finding which nodes are the most important for holding the network together. Again, Anakin, not a good connector for the Star Wars network, although he has a high degree centrality score. Betweenness scores are also good indicators of which nodes could have the most control over social, communication, travel, or transport networks, again, because they do control more routes passing through them. A caveat here to kind of keep in mind is that a high betweenness score doesn't necessarily mean that that person or whatever, object in your network has the most power or influence or information themselves. They could just be the one connecting point between a cluster and the larger network. They could be on the periphery of both. Closeness centrality is another score that you can look at. This is also related to shortest paths, like betweenness, but in this case, we care not about how many shortest paths are passing through a node, but we want to know how close is a node to the rest of the network. So on average, how far is it away from every other node in the network? What is the average length of the shortest path between a given node and all the other nodes in the network? In comparison to degree and betweenness, when we're looking for high scores to indicate the most important nodes, with closeness, we want a low score. The closer a closeness score is to 0, the closer it is, that node is, to all the other nodes in the network. And in that sense, it is central because it is close. A good example of this is airline routes. So it's of course not always possible to fly directly from one airport to another. So for, this is Delta's route map, of course. We could, given this network, calculate which airports are the most closely connected by measuring how many hops you have to take to fly between two cities using that carrier. So we would expect Delta's big hubs in JFK, LA, Atlanta, Detroit to have the lowest closeness scores because it's easier to get directly from them to anywhere else in the network than it is from smaller cities like, Buffalo or this place in Idaho or Montana. Wow. Too many things plotted on this map for me to see the underlying geography. So this is a great closeness score, or centrality score to use when you're looking for key distribution points in delivery or transport networks or in social networks to find the broadcasters who are able to quickly get messages out across the whole network. The big caveat here is if your network is directed, the shortest paths to and from a node are different lengths. So if you imagine you could only fly into some airports, but you couldn't fly out of them, that would be terrible. But that's the caveat here is one node could have a really high outgoing closeness value, you know, and a very low incoming closeness if lots of paths lead to it, for example, but it doesn't lead anywhere. And then finally, eigenvector centrality. So this sounds complicated, but really it's just a nuanced version of degree centrality. That's maybe not fair. It's a lot more nuanced than degree centrality. And in fact, it's one of the best all-around measures of centrality in available in network science. So what eigenvector centrality does is measures each node's connection to each other node, like degree. We're counting up how many nodes you're connected to, but rather than just counting how many nodes, we also care whether or not we're connecting out to other nodes that are themselves highly connected. So with just degree centrality, a node, for example, gets 1 point when it's connected to other nodes, but not all nodes are equally connected. So with eigenvector scores, connectedness to other highly connected nodes increases your score. So it's not just about how many people you know, it's also about who you know. Google's PageRank is an excellent example or parallel of this. It's obviously not the same, and it's, well, the big tech search algorithms are changing, it feels like daily. But at some point, you know, it was true to say that this algorithm, you know, pages were ranked more highly and appear higher on your list of search results if a lot of other pages linked to them that are also themselves highly linked, taken as a rough proxy of quality on the internet. So if it's hard to think about this in terms of websites, you might also think about it in terms of books and citations. So the more a book is cited, the better, but the more a book is cited by other books that are themselves highly cited, perhaps a rough proxy for how large of an audience a book has in a scholarly community, that's what eigenvector scores are all about. Again, a great all-around measure for how well connected a node is. And there is another question in chat. The difference between closeness and betweenness. Yes, absolutely. So I'm just going to go back up here. So they're both about, in fact, I'll go here. They're both about shortest paths. Betweenness is how many shortest paths pass through a given node. And closeness, and we care about high scores. So a high betweenness score means that you are situated between, on the path, the route between a lot of other nodes when they're trying to communicate with other nodes. Whereas closeness is not how well of a connector you are, but how immediately can you connect out to all other nodes. So it's the average length of the shortest path between you and the rest of the network. So we don't care then about how many shortest paths are passing through you. It's literally how directly connected are you to the rest of the network. Yeah, and it's going to be a lot easier to kind of, I hope, visualize this when we are actually visualizing the network data in Gephi. All right, so that was really the bulk of the network, the graph theory. Two other really common questions, because that was all about nodes and importance of nodes, really understanding, you know, who are the actors or entities, again, you can substitute out, if you're not looking at social networks, for example, you know, the infrastructure or whatever it is that makes up your network that you care about. But we're talking about centrality scores, we're talking about individual nodes. With network density are questions like, how strongly connected is my network? Now we're moving out to a network level metric that's describing the entire network structure as a whole. So these kinds of things are important for comparing across networks, comparing multiple networks to each other. So network density is a great way to do that. So network density is a measurement indicating the potential connections that it's a percentage of the potential connections that actually exist among the nodes in your network. So the formula is for, you know, if your network has 20 nodes, each node could, in theory, connect to 19 other nodes. That would, if all nodes were connected to all other nodes, a network would be said to be 100% dense. So it's given as a percentage or a decimal, a fraction. If only a few of the potential connections actually exist, then the network is said to be looser. So again, this is all comparative, and there's no fixed number that's, you know, some magic threshold for, yes, now the network is dense. It's all about within the particular kind of network that you're describing, for the size of network you're describing, et cetera. How does it measure up to other networks? So the metaphor that I like to use here is, you know, a dense network is like a family reunion. Everybody knows everybody else, or knows somebody who knows somebody. It's you're in theory related to everybody there in some way. Versus a looser network, a less dense network, is like everybody riding the public bus together. All right, another question. Would the number of possible nodes be calculated with something like a power function? It is simpler than that, and we can actually look at the formula later. I believe it's, I don't even want to say it out loud because I'll be wrong. I think it's like n times n minus 1 divided by 2, but don't quote me on that. But in any case, you end up with a percentage number that kind of describes the overall structure of the network. Another really great question to ask, and that researchers often ask about networks, are there detectable clusters or communities within this network? N times n minus 1 divided by 2. Is that what I said? If I was right, I would be amazed, but I will definitely look that up for you all later. All right. So network modularity is a calculation that does that identifies communities, also called modularity classes, in a network. Another network level measurement that can be helpful for understanding the overall structure, and perhaps for comparing networks as they change over time, or for comparing networks against each other. So at its heart, back up one. At its heart, and this is a much more complicated algorithm, and it's not even fair to say algorithm. It's implemented different ways in different tools. Many folks have written algorithms for computing network modularity. It's, yeah, we can look at the one that Geffy has implemented. But the way it operates is essentially by comparing your graph and the specific ways that your nodes are connected to each other in your graph to a network created at random of the same expected size and connectedness. So the comparison of the number of edges, where the edges are in your graph, to a randomly inequivalent but randomly generated graph is what allows the computer to kind of identify, and it runs this, n number of times. You can select, usually you'd run it like 100 times at least to kind of generate a model. So again, a network level measurement that can be generally helpful to do. It doesn't work at all or well with weighted or directed graphs. That said, you can run the modularity algorithm in Gephi. It just won't take edge weight or edge direction into account. And the reason that that complicates things is edge direction and weight significantly affect how a node is connected to the rest of the network. I believe there are implementations of modularity that do work better for weighted or directed networks, but the one that we're going to be looking at in Gephi, that's just a caveat to be aware of. This has been used for things like detecting communities, sub-communities. This is, for example, a network hairball. This is accounts that tweeted using a particular conference hashtag, a conference I attended back in 2019. And they tweeted to each other, or the graph also includes accounts that were tweeted about, but who did not tweet themselves. And it's colored by modularity class. So there were detectable clusters of people who spoke more to and about each other than they did about the rest of the network. And it's interesting to see how that kind of breaks down along disciplinary lines, or in some cases, it's folks who went to the same graduate program, or, are co-publishing, on a particular, with a press together, or things like that. So this is essentially how it's one example of how this has been used for citation-like networks. But it can be used many other ways. All right, I'm going to pause here because that was the spiel in terms of basics about terminology and some of the network calculations that we'll be playing within Gephi. But I do want to give folks a chance to throw questions in chat. Just in case we've had folks join us, there is the link again to these slides and the network data we're about to play with. Yes, that very last example was made with Gephi. It's a great question. So there's a question in chat: how do network modularity algorithms know which nodes should belong to the same group? And the thing is, kind of like any machine learning algorithm, each time you run it, or if you run it as it's implemented differently in different tools, you'll get slightly different results. So it's again comparing what your network looks like versus what the computer expects a network to look like if it was random. So if your nodes are more closely connected to each other than they should be as expected in a random network, that's when the computer is going to identify them as being in their own modularity class together. Where the boundaries fall, again, you can play with parameters and the modularity classes will shift slightly. So that's why it's so important to document how you're running these, what the parameters are that you run any of these calculations on. Because as we'll see, changing very small things, removing 2 nodes from a network can entirely change the results of the network metrics that you gather. How old is Gephi? That's a very good question. It runs using Java version 7 or 8. I don't know if that tells us anything. I believe, let's go to Gephi here. So, what is Gephi? Oh, thanks, Seth. Seth in the chat shared initial release date 2008. It has, so let me talk a little bit about what Gephi is, and then we can pop over to look at the actual website and downloading and installing it. So Gephi is the open graph viz platform. It's not the only open source network visualization platform, but it is one of the most commonly used in, again, humanities and social sciences. I prefer to use it because of all these reasons that I have on the screen, that it is free and open source, that it has a robust user community across different scholarly and academic communities and across different countries and languages. It has many plugins that have been created to extend its functionality. And it's one of the few tools that has both a fairly straightforward graphical user interface and built-in calculations that are very transparent with citations, in terms of which algorithms and formulas they're implementing for all the basic network analysis, like calculations and some of the more advanced algorithms. So centrality, density, modularity, and several others we just did not have time to talk about today. And of course, you can get data into and out of it in a variety of different formats. Great question in chat. How does it differ from tools like Tableau? So this is specifically for network data. And that's a great segue into what network data is. So I think it makes sense. I'm going to do this real quick, and then we can go and look at how to get Gephi. But because the question was asked, Gephi and many other tools, either command line tools, tools that are packages and libraries in R and Python for working with network data, the vast majority of them are going to require data that is in a specific format. Gephi requires 2 files if you are generating a network graph from scratch, and that is a list of your nodes and a list of the edges, the connections, the interactions between those nodes. So it's going to expect you to, if you're, again, creating something from scratch and not opening a graph file, which we'll look at, it's going to expect something that looks like this, a spreadsheet that's got at least a column for a unique identifier. In fact, ID and name could be the same as long as your nodes, whatever you're using to describe your nodes, are themselves unique. If there are any duplicates in here, things get funky. So it's always best to go with a unique identifier field that is distinguishable. And then optionally, any other attributes you want, any other variables describing your nodes. So in this case, these are characters in the book, Les Miserables, and we have a gender field. The other file that Gephi expects is called an edge list that also requires 2 columns. You absolutely have to have a source column and a target column. And these are using the unique identifiers from that node list. Again, if your ID column over here just has, the names of your things, you can just use the names of your things in the source and target columns as long as they are unique. You can specify here whether your graph is directed or undirected, and then how do you assign the weight? So in chat, can you clarify, do you mean how are these numbers determined, or, because this is, okay, who knows? So that depends on your research, right? So we'll look at some data sets where there is a weight column and for squirrel interactions. That's why it's so important to have a code book or document your data, because there's no way for me to know, looking at this data, how this weight was assigned. So I believe for this data set, it is how many times because there's only one example of each interaction. So they're characters in a novel. How many times did those characters speak to each other in the novel? It could also be how many different pages do they appear on together? How many different chapters are they in together? You specify. That's again, up to your research. You can also give your edges their own unique identifier. Yes, exactly. ID in the edge list is the ID for the edge. So for this interaction between Muriel and Napoleon. Yeah, so you could totally have, so weight, again, if your network is comprised of letters being sent between different people, it could be how many letters were sent. It could be, the kind of letter. It could be like a qualitative descriptor. So the weight of an edge is determined in lots of different ways. Really, really good question. Okay, so that's the very brief primer on network data. We'll talk about it more as we get into Gephi. So to access this tool, you can go to gephi.org. I'll go ahead and just pop this link into chat in case anyone is interested in playing with it now. I'll come back and answer that question about directed versus undirected in a second, if that's all right. So in order to install and run Gephi, you will need to download the installer, as well as ensure that you have a Java JRE on your system. Gephi works with Java 7 and 8. So they link out to the Get Java page. If you navigate over to java.com, and the download over here, you don't need the full SDK, you just need a runtime environment. So it should auto detect which one you need, and then you can download that from the good folks at Oracle. Yeah, and so for folks on Mac OS X, I believe you do not need to separately install Java, but if you're running this on Windows or Linux, you will need to ensure that Java is installed on your system. There are sometimes issues running Gephi for the first time, which is why I wanted to make sure to call attention to this resource here and this page, the installation instructions. Sometimes Gephi doesn't know if it looks in the default place for where it thinks Java should be installed on your computer and it's not there, it can't run. So it will give you an error message saying, I can't find Java, basically. So you'll just need to follow the instructions here on the installation page to point Gephi at wherever you installed Java for you. Can I post the Java link? Yeah. All right, so that's how we get Gephi. There's also a variety of resources here on the Gephi website. You can access the documentation for Gephi. You can also, if you click on Learn, there's a number of different resources, tutorials, getting started guides. There's a specific guide for supported graph formats that explains a little bit about each one. And I mention this because you'll very likely encounter network data in the wild that is stored in a variety of file formats. and they're not all equal. Some of them are text-based and may not store information like the position of nodes. So basically the visualization aspect of like, where are the nodes? Some of them will. If they're XML based, like GraphML is a really, really good one. That can store the node layout. Let's see. And thanks so much for noting that, Bart, in the chat, that, yeah, I believe Java does not need to be installed separately for folks using Macs. All right, so that's how we get Gephi. I'm gonna go ahead and pop over here to Gephi. So it's already running on my computer. I am running version 0.9.2. That is the most current version, which again requires Java version 7 or 8. And when you launch Gephi, you'll get this welcome screen that will give you a couple of options. You can start a new project or open a graph file. Or there's a couple of examples actually in here. And in fact, these are using different file formats. So we'll note, if I open up, I'm just going to open this up. I believe GML does not store. Yeah. So if you open up a graph file that is in GML format, or another text-based file format, you'll likely see something like what I have on my screen right now, which is a hideous hairball that is not helpful in any way. And in fact, if you create your own, if you start a new project and you bring in nodes list and edges list, which we'll do next, you'll also get this. This is the random layout. So by default, Gephi doesn't know where to put nodes. It's going to just throw them on there. So we will have to go through the steps of telling the program how we want to lay out the visualization of the network graph. But before we do that, let's just take a look at the interface here and what it looks like. So we have essentially 3 windows in Gephi. Right now we're in the overview window. This is where we're going to spend the majority of our time. This is where we can customize the appearance of our nodes and our edges. We have our canvas here where we're seeing the rather unusable network graph visualization. We can customize our layout down here and run different layout algorithms. And then over on the right-hand side of the overview, we just get this little context, like how many nodes and edges are there. And then there's filters and statistics. So filters allow you to subset if you only want to view or run calculations on part of your network. You can filter out some of your nodes or edges using filters, essentially hide some of them. And statistics is where we're going to run all of those calculations and other more advanced algorithms like modularity. We also have the data lab, which is the second window in Gephi. And this is an interactive spreadsheet view, tabular view of our data. And so I opened this up as a GML file. It was one of Gephi's samples. So we have here in the data table, we have our nodes list and our edges list. So we can switch between those. And right here in the data lab, you can do a lot of things. You can do some lightweight data manipulation, data processing. You can add nodes and edges. You can change them. You can import and export right here in the data lab. I would typically not do a lot of bulk processing in Gephi. I would choose to do that in spreadsheet software or something like OpenRefine, which here at UCR, our data librarian, Kat Kosher, actually just did an OpenRefine workshop and is a great resource. If you're curious, she teaches OpenRefine here locally, and I'm sure there's somebody locally who teaches it wherever you are. Yeah, this is here to do some lightweight data manipulation if you need to. I really like that this is an option right here in Gephi. You don't have to be constantly moving back and forth if you need to make small changes to your data. You can edit like right in here. And then finally, the third window is the preview window. We can, I mean, if we wanted to print our very ugly hairball, this is essentially like a print preview. This is especially useful if you are going to be generating a lot of network graphs and you want them to share as the same visual style, or you want to export them all using a certain kind of theme. You can use the presets in here or create your own custom themes in terms of how the edges appear, if they're using straight lines or curved lines, what font, all those sorts of things here in the preview window. But again, we're going to spend most of our time over here in the overview. All right, so this was just an example I pulled up to demonstrate the interface with. So let me go ahead and delete this workspace. We no longer need it. So now what I'm going to do is open up one of the data files. So in the link that I've been sharing in chat, where the slides are located, you should have access to 4 different data sets. We've got a kind of literature example, an example from that uses citation analysis. We've got, I mean, my personal favorite are these Squirrel social networks, as well as an example subset of the Western US power grid. So we could look at any of these. Yes, let me just grab that link again. Okay, I see a vote for squirrels. Anyone else have a strong preference? Let's start with squirrels. We can go elsewhere. So I really love this study that I found. In fact, there's an entire, I've got some slides later we can look at, actually not too much later because we're getting up there on time. But there's a data repository called the Animal Social Network Repository. Lots of really fascinating network data sets to explore. But these are California ground squirrels. It was a study performed at Mills College over 2 years, 2016 to 2017, where they viewed above ground social interactions and below ground using radio frequency tags of the squirrels. So, and they detected differences in their social interactions in the above ground network from the below ground network using things like Betweenness Centrality scores. And, you know, in fact, they found, I think in the below ground interactions, female squirrels were more central to the strength of the network, and they use different metrics too. So I've got the citation in there. It's a really fascinating read. So I'm going to open this up. It is a GraphML file, and I'm going to just add it to a new workspace. So we've got something that looks like this. Just some very basic points here with Gephi. I've been zooming in and out using a mouse scroll wheel. There are a bunch of buttons over here that kind of change and toggle how you interact with your graph. It can be very challenging to use this software with a laptop trackpad. I found personally that I need a mouse to be able to use this successfully. But we can, for example, change between a selection pointer where I can right click and select this node in the data lab and then hop back over. So it's really easy to move back and forth between the overview and the data lab to view details. So again, each of these is a squirrel in the nodes, and then each edge is a social interaction between two squirrels, given some weight. And again, I'm not certain what this weight is. So the first thing we might want to do is to run a layout to make this a little bit more visually apparent what's going on. So there's a variety of different layouts in Gephi that are built in. And in fact, you can add more very simply using Geffy plugins. So you can add more by going up to tools and going to plugins, and you can group them by category. That's odd. This might be something strange with my internet. Oh no, that's updates. Just kidding. Available plugins. There are several here. So if we just look for layouts, these are all additional layouts that you can add that other people have created. And it's, yeah, it's a very good idea to kind of just check and see who's making the layouts and how they're being made. Question in chat. So the question in chat has to do with layouts in terms of, can you draw it without edges intersecting? So there are a variety of different layouts, and the vast majority of them do what you're describing in terms of avoiding overlapping. And in fact, there is, yeah, we'll look at one in a second. So there are a couple of different ones. Force Atlas 2 is a very good general starting point for large networks that also spatialize them to enhance readability. So this is going to bring together nodes that are connected and space apart unconnected nodes. You can, of course, play with all of these different parameters. So for this one, prevent overlap is a good one to check, and then you just hit run. Some of them will run, they'll keep running. Okay, stop. Some of them will keep running until you hit stop. Others are one and done. So something to play around with. There are others that do the exact same thing. I'm just going to reset this one by doing random again. So we've got our hairball. Another very good one is Ifanhu. This is a layout algorithm that is very good at scaling and emphasizing clusters. So that one ran and then it was done. I didn't have to hit stop. So it's got similar results, but it's a little more dense. I have an extra layout here that is installed called no overlap. So I'm going to run that to ensure that there are no overlapping nodes. But of course, there's plenty of edges in here that are overlapping. So if you're going for a particular, each of these layouts has a different strength. I suppose is all I'm getting at. Yes, and there's expansion and contraction algorithms if you just want to space things out a little bit. All right. Yeah, so that's the basics of layouts. We can also, before we get to appearance, because appearance is a huge thing in terms of making the graph more readable and also helping you in your kind of exploratory data analysis, understanding using the visual layout of the graph, understanding aspects of it. But first, we want to run some of these network statistics. So we want to calculate some of the basics within network overview and node overview. So we want to run average degree. Average degree for the squirrels is 8.6. And what was n? Yeah, so we got 61 squirrels with 265 interactions. Since this is a weighted graph, we could also run average weighted degree, which is a lot lower, because I believe the vast majority of the weights were less than 1. We can run, in order to get betweenness centrality, closeness centrality, any of the shortest path things, we have to run network diameter. So here's something to note, and this was something that was asked earlier. Why are sometimes the centrality scores integers and sometimes not? You can normalize them. This is a bug in Gephi. Whether or not you check this box, it does not matter. They will be normalized. So we're not going to get a value like a betweenness centrality score of like 27 for any squirrels. It's going to be between 0 and 1, which in fact I would want to do. But and this is something to note too. We have in our graph this little cluster of 2 squirrels who didn't socialize with the larger group of squirrels. So they're actually throwing off some of our network statistics that are describing the network as a whole. If we ran the network diameter on just the connected portion of the network, we would get different results. So right now we're getting a network diameter of 5. That is what is the longest, shortest path across the network. And then radius is what is the shortest path. The only way you get a radius of 1 is if the shortest path is 1 person away, meaning the diameter should be 2. So this is itself its own little network over here, and it's throwing things off. So the way, and we get betweenness centrality, closeness centrality, and other things we didn't have time to talk about. So the way we could deal with that, we could go in and we could delete these nodes, we could remove them. We could also filter them out. So what I want to do, let me go ahead and calculate things. So as I'm calculating these things, what we're doing over here in the data lab is expanding our data set. So whereas before we just had up to here, we had through Fermark information about our nodes. Now we have all these other values calculated for our nodes. And for the purposes of this particular chart, I happen to know that the eccentricity is odd for the 2 squirrels that are over there in their own cluster. There is no simple way. What we could do is we could go in the overview and I could manually identify them by right-clicking on that squirrel and selecting in the data lab. It's this guy, Pirate Hook and capital E. Are throwing off all of our scores. So they have an eccentricity of 1. Eccentricity is another thing that is related to shortest paths. It is, I'm blanking on, I think it's, no, it's, yeah. I'm blanking on what eccentricity is. I apologize. But essentially, I know that we can filter out because these are the only 2 squirrels with an eccentricity score of 1. So we can go into filters and I'll point you to the Geffy tutorials and resources for why this looks the way it looks in here. This is quite confusing. This is perhaps the most confusing aspect of the interface. If I take fault with anything, Geffy, this is it. So under attributes though, so we can essentially filter by attribute. So we're going to filter by the attribute eccentricity. Partition is if we know the specific value that we want to filter by. So we want to accept all eccentricity scores except 1 and filter. So now those nodes are not visible. So if we go back over to statistics and we rerun network diameter, you can always hit the question mark to bring it back up. So our previous results were 5.1 with an average path length of 2.41. Now if we rerun on just the connected portion of the graph, we get diameter of 5, a radius of 3. This is more expected for this size and shape of a network. And the average path length hasn't changed that much. It's been probably changed over here. But importantly, that radius isn't being thrown off, and neither are any of our other calculations. So that's just one example of ways things can be thrown off. In terms of changing appearance, now that we've got some of these calculations, we can go over here into appearance. We could change the color and the size of our nodes or edges to reflect different values. So for example, we could, and unique is just one absolute value. If you wanted to change all the nodes to be red, you can do that. Partition and ranking are if you want to color or size by a variable. And partition is if that variable is categorical. And ranking is if that variable is sequential. So if we are coloring by, for example, sex, we would want to choose partition because that's a categorical variable with one of 2 values. If we try to partition color by something like Betweenness Centrality, we're going to have too many colors. It just gives up. But we could do ranking by Betweenness Centrality, and it'll give us an option to create a spectrum. So we could choose a couple of different color palettes, gradients or scales. This is not a palette, this is the scale. So that is an option. So we could apply that. So now the darkest nodes are those with the highest Betweenness Centrality, which makes sense. So we've got this squirrel here who is connecting this portion of the network, these 2 squirrels, in fact, to the rest of the network. A lot of shortest paths go through the 2 of them. We could, however, if we wanted to color by another variable. We can also scale the size. We cannot size based on a categorical variable, but we can scale it based on something like Betweenness Centrality. So this is a little more. We're getting to a point where the appearance of the graph is actually telling us something. And can we make the edge width or color depending on weight? So currently, weight is already being represented. We could change the appearance of the edges based on different things, but I believe the default is to scale this, and we can go in and change the scaling. But all right, so that's layout, appearance, and some of the basic ways to visualize. Importantly, how do we get this data back out? So there's a number of different ways you can export the network data. So now that we have added a variety of calculated values to this data set, we may want to export the table itself. So we could export our nodes and edges lists right here in the data lab window using export table. You can save it out as a CSV or I believe an Excel spreadsheet. And under preview, you can actually, once you've decided on whatever visual style you're going for, you can export an image of just the graph. So you can export as an SVG, a PDF, or a PNG, an image, which can be helpful for publication purposes. And you can also save your project out if you want to, again, save things like the color, size, position, and layout of your actual network graph. You'll need to use a file format that is capable of storing that information. So that means saving as, you could save as a Geffy project file in the same way you would save, an Adobe Illustrator or Photoshop project that's in progress, but then you are limiting yourself to opening that file with Geffy. You can also save out your network data as a .gexf, and I'll refer back to this page here, the supported graph formats. Gexf is Geffy's, oops, oh, that's not great. We'll have to go track down the correct page on their newer wiki. But that is the formatting standard that Geffy uses for encoding network data. And then GraphML, in fact, there's this lovely little comparative table down here. If you want to save visualization attributes, certain files formats will allow that. So GML allows some visualization attributes. But GraphML is a very good option. Okay, questions? Let me move back over here to the slides just to wrap up, and I'll stick around for a while if folks have questions, but I wanted to point before folks head out to a few specific resources. I have links on this slide, which is again accessible at this short URL, to a few selected Geffy tutorials, including those that we have already pointed to on Geffy.org. There are a couple, and there are some available in a variety of languages as well. If you prefer tutorials in French or Spanish, or it's a couple of other languages. Network analysis learning resources. There's a really, really wonderful open textbook on open science network science that does a really good job of walking through real life examples on the applications of different network calculations. And for more of a digital humanities approach, I've linked to a series of blog posts by Scott Weingart. And then there's a couple of places here. Really, there's so many places. I would point you to your local data librarian or any of the other amazing workshops that are being held this week through UC Love Data Week. There are a number that are going to point to other places to find and share data openly. There are so many places that it's hard to point to just a few, but these are some curated kind of lists of other lists that include some really excellent places like the Stanford Open Network Data. Irvine's gotten a fantastic open network data repository, other places like that. And yeah, I'll stick around. Happy to answer more questions. Just going to paste this link in chat if folks have 30 seconds to take before you head out. It's very helpful for us here locally at UCR to hear from you all if you're able to take a very, very short 2-question survey. So thank you.